Hello everybody, my name is Chris Dowger. I'm an electrical engineering undergrad at the University of Buffalo, and today I'm going to talk about fault tolerance methods in field programmable gate arrays, or FPGAs. So what is an FPGA? An FPGA is comprised of arrays of programmable logic blocks, or PLBs, that are associated with each other by a programmable routing grid or a matrix. The configuration of the FPGA defines its functionality by identifying which blocks and wire portions are going to be utilized. Currently, static random access memory or SRAM FPGAs are the most well-known and common. This is due to their high number of reconfiguration cycles and the relative simplicity of programming on the device. Here's the basic architecture of an FPGA. You can see the PLBs are connected to switch boxes by wire segments and then connected to the connector boxes. A PLB is going to be made up of multiplexers, lookup tables, flip-flops, or basic logic gates, pretty much any digital component that you can utilize in your circuit. The PLBs will be then connected by the wires in any pathway that needs to be done to get a specific output that is required by design goals. Most digital devices will suffer from a manufacturing imperfection or just begin to degrade over an extended period of usage. This is known as a fault. In definition, a fault is a physical event inside an FPGA that forces it to break down and ultimately stop running. Faults will tend to either happen at the beginning or the end of a device's life cycle. These manufactured faults or imperfections are typically created by contaminants or other interferences that will occur within the manufacturing procedure. This can include dust or other particles getting onto the board and interfering with connections or wires, causing the board to malfunction. In order to overcome these faults, users or even manufacturers will develop fault tolerance techniques that will allow them to overcome a fault in the system. These devices are usually categorized into device level and configuration level programs. A device level method is usually programmed right onto the FPGA using additional PLBs that will allow the fault to be maneuvered around so the output can stay consistent. A configuration level method is usually software-based design using outside injection that will allow it to run a simulation that will locate the fault and allow it to be repaired or bypassed in order to continue operation. Configuration levels are usually a bit slower and require the device to be off in order for the simulation to run, whereas a device level will use more PLBs, which ultimately takes a lot of overhead area on an already cramped FPGA. There are two components that define a good fault tolerance method. These are fault detection, which is the ability to find the fault and bypass it, and fault repair, which is the ability to either fix the fault or disregard it altogether. As with any problem, the first step in fixing it is detecting where the problem is manifesting. This is known as fault detection. Fault detection is used to inform the user and the system where a fault is so that it can be repaired or bypassed entirely. This is usually done in a single step or a multi-step process depending on what type of test is used. Common types of detection are redundancy error detection, offline testing, or roving test methods. A redundancy error detection will utilize multiple PLBs in the same structure to give multiple outputs and using the best output from the system to be processed as the primary operation. An offline test is a built-in self-test model that will run and analyze multiple PLBs when the FPGA is not in operation. A roving test method builds upon the offline test but can be operated at the same time the FPGA is in operation. This allows for the PLBs that are not in use to be checked while the main operation is coming out with an output that is desired. The graphic here shown is a triple module redundancy check. It's a form of redundancy error detection that requires multiple PLBs to test for the output. What will happen here is you can see there's three different modules. Each one of these modules is the exact same, and what will happen is an input will enter, run through all three modules, and come out with an output. The output is then going to be checked for consistency or equivalency, and it has to equal what the design goal is specified. The best output will be the one that goes through the system and ultimately is outputted by the FPGA. The table here is a summary of all of the fault detections that we talked about. You can see that what we're categorizing here is the speed of detection, resource overhead, performance overhead, granularity, and coverage. Each of these is their own property that are either make the fault detection viable or unviable depending on what you need and have room for in the system. For example, if you're running out of space, you don't want to use a modular redundancy check because it is going to take up a lot of resource overhead. Basically, you're going to have to double or triple the amount of PLBs that you're using. However, if you want something to detect a fault extremely quick, you would use the modular redundancy and not use something like the offline built-in self-check. This is because a built-in self-test can only be used while the device is not in operation. For the next part of this video, we're going to talk about fault tolerance methods that can overcome the previous mentioned faults. One of these methods is pretty basic. It's called extra rows, and what it does is it adds multiple rows of PLBs and wire segments that are necessarily the same thing, but they can take over in the event of a fault in a certain section. So if you see, the row decoder will spit out a row 0, 1, 2, etc. And then if a wire segment in that column becomes faulty, then the column over will take care of it on that row. So basically, if you look in the top left section, you'll see a defective wire segment in row 2 of the first column that is accounted for by row 2 of the second column, and so on. Another form of fault tolerance method is known as SRAM shifting. SRAM shifting is the process of taking combinational PLBs and just shifting them over logic blocks. So basically, you can see in the diagram that the first implementation will use the middle 2 rows and columns. Then, if you detect a fault in the first column, you'll shift it over logically to the right one, and it'll use the same setup but just different PLBs. And you can see that in figure 3 and figure 4, where it just shifts the vertically by section. This will allow to just bypass the fault entirely. However, it does bring a drawback in utilizing a lot of space because all of these PLBs need to be equal, just in a different spot. A third form of fault tolerance methods is cover segments. Cover segments, like extra rows, utilize the same process by adding a spare cell, as you can see in the figure. These spare cells will cover the cell before, so that way if there's a problem, then it'll connect to that cell and bypass the cell with a fault. Such as cell A will have cell B as a cover segment, so if cell A has a fault in it, cell B will become the next cell A and the whole device will shift over. Therefore, cell B will become cell C, and cell C will become cell D, and cell D will move into the spare cell. Evolutionary methods are important fault tolerance mechanisms because they allow the system to adapt to whatever fault is present in the device. This works by using combinational logic circuits such as 3x3 adders and 3x3 multipliers, which can be shown on the left and the right respectively. These basically use all of these digital components such as adders, lookup tables, decoders, and multiplexers in order to generate an output that is equivalent to what the design goal is specified for. Therefore, if an FPGA has a problem in section A, it'll use these combinational logic circuits to get section A through a different means and continue to output precisely. The drawback with these is these logic circuits require a lot of space that the FPGA is not using. Here you can see a comparison table for the fault tolerance mechanisms that we described before and some that we didn't talk about. You can see that we're testing for a couple properties that will determine the feasibility and applicability of the fault tolerant method in our FPGA system. Basically, we're testing for a fault pattern tolerance, which is what types of faults and what variety of faults can be detected by the system and fixed. The resource overhead is the area that the fault tolerance method needs on the FPGA in order to work. The performance overhead degradation is how fast it takes for the fault tolerance mechanism to fix the problem and get it back to full optimization. And the complexity of repair is the ability for the fault tolerance to pinpoint the location of the fault, so that way if repairs need to be done on the device, the user will know exactly where it needs to be done. So for something like a hardware level, it's going to have a pretty poor fault pattern tolerance because they're designed to just take care of basic, simple faults that can only occur in these places. So with something like extra rows, if something happens in a different section of the FPGA, then it won't be able to account for that in the extra rows because they're already predetermined. And it's also going to require a good amount of area overhead because it has to have multiple implementations of the same PLB. Something like evolutionary fault tolerances are really good at detecting multiple faults because there's just so much logic behind them, and they can be changed and shifted based on the amount of multipliers and PLBs that are being used, that they can detect a wide variety, and they have extreme flexibility in finding faults. However, because they have to require a lot of PLBs with different digital components, they require a large amount of resource overhead, which can make it hard to find an FPGA that has what you need for it. Also, with the complexity of repair, something like a hardware level is going to be really easy to repair because you know exactly where the fault is because it's just going to show up in the row. However, with an evolutionary fault, you might not know where anything is because there's so much logic being multiplied and passing through multiplexers and lookup tables that it's going to make it hard to pinpoint the exact location. Fault injection is a useful tool for testing how well your fault-tolerant system works on your FPGA. It basically uses a simulation that will inject faults and receive feedback on how the fault affected the system and what the system did to fix the fault. Basically, it uses source codes, so any C or C++ program that will allow you to implement a fault whenever and wherever into the system in order to get these results. How it will work is you can see from this table below that you will input a constant value, and then this constant value will input that fault type at a location of your choosing. This is an example of the fault injection process. You can see that you create your source code, you generate your source code, and then you inject it onto the FPGA. You trace your data or see if you get the golden trace data, which is a perfect 100% overcoming of the fault, and then it will run through the result analyzer. Okay, so all in all, we learned that a fault is a damaged or failing PLB or part of an FPGA. Fault detection is used to find the location of the fault within the system, and a fault tolerance is the process of fixing that faulty part and getting it back to complete operational standards. Things to consider when picking a fault tolerance program is the overhead area usage, the speed, the complexity of the repair, and the accuracy of the repair itself. And so this makes it that it's really up to the user to determine what kind of fault tolerance method they need, because if they're already cramming into space, you won't want to use a tolerant that requires extra rows or something when you don't have that much space on the board itself. And then in order to test your fault tolerance methods, you can use a fault injection tool to see just how well your device will continue to operate if it encounters specified faults. Thank you very much for listening. For further study, I encourage you to look at the following links.